Hello everyone, welcome to this class. This is Teacher Simon taking you through AS Chemistry paper 9701/13 for May June 2025, and this is part 1 for questions 1 to 22. Question 1. Which isolated gaseous atom has a total of 5 electrons occupying the spherically shaped orbitals? The orbital that is spherically shaped is the s orbital. Okay, so let's look at sodium. Sodium is in position 11. So electron configuration is 1s2, 2s2, 2p6, those are 10, and then we have 3s1. Now, for s, we have this one here, we have this one here, and then this one here. How many are they? Here we have 2 electrons, then plus 1, those are 5. And they said that we have a total of 5 electrons occupying the spherically shaped orbitals. That means our answer actually has to be A. But let's try B. B is fluorine. Fluorine is 9. So we have 1s2, 2s2, 2p5. Not so? And then when you add these ones, they are 4. So that one will be off. Then boron is in position 3. So that is 1s2, then 2s1, and these are 3. Then lastly, we have potassium, which is in position 19. So 1s2, 2s2, 2p6, 3s2, 3p6. Also, these are 18. Then we shall have 4s1. Okay, so these ones, how many are they? 4, then 6, and then 7, but we need a 5. So the 5 came from A here, so the answer was A. Question 2. Diagram 1 shows the reaction pathway for a reaction. Diagram 2 shows a graph of concentration of reactant against time for the same reaction. When you look at this one here, we see that the products have gotten less energy compared to reactants. That means this is an exothermic reaction, okay, because there is energy that is lost to the surrounding. So what is remaining as the products, they are going to have very little energy. So when you look at here, the enthalpy change, okay, here is negative. You see that? So it is an exothermic reaction. And then diagram 2 here shows the graph of the concentration of reactant or the same. So as time goes, the concentration of the reactant, of course, reduces. Okay, it reduces because you are producing products. Okay, then next they are saying which diagrams drawn to the same scale show the effect of increased temperature on this reaction. Now, when you increase temperature, first of all, the rate of reaction increases because these particles are going to gain energy. So we are going to have many more molecules having energy that is greater or equal to activation energy. Are we there? So you are going to have then more successful collisions. So the rate of reaction increases generally. But then since this one is an exothermic reaction, then it is going to slow down this process. Okay, it is going to slow down. In other words, it is going to favor the backward reaction. Okay, so in such a case, we are having an equilibrium reaction, maybe like that. Okay, and the one that is forward is exo, and then the one that is backward is endo. So when you increase the temperature, you favor the endothermic reaction, which is the backward reaction. So first of all, the rate of reaction increases. If the rate of reaction increases, when you look at this one here, if I may, let's say, draw a tangent at just one point like that, and then there is this other one here. If you are drawing a graph of this one with an increased rate of reaction, then it has to bend more to the left here. Okay, this is the original one, but this is the new one. Okay, it has to bend to the right because what are we seeing here? That in just a short time, the concentration of reactant decreases. You get it? But since this one is an equilibrium reaction, it decreases very fast. But then again, the one for the endothermic, that rate of reaction is also going to increase. So these two actually increase at the same what? Rate. But because it is exothermic, the reaction is exothermic and you are increasing the temperature, then the endothermic reaction is going to be favored and you find the equilibrium shifting to the left. So just as the rate of the reaction, the equilibrium is reached faster. Okay, so we expect this one here to be bending to the right, to the left, so that when you draw the line, this line is steeper. So when I have a line like this one here, and then I have another one like this one here is steeper than this. Why? Because for a shorter time, very small change in time, here we have a bigger change. And then here, you're having a very big change in time. And then you have here, okay, let's say also there we are having a big change, but it is small. So small divided by big, you get something small. So the gradient is smaller. That means the rate of reaction is slow. And then when you come to this one here, big divided by small, you will get big. That means the rate of reaction is higher. Does that make sense? Okay, so that means when you look at all of these graphs, for this graph here of this for diagram 2, we have to look at when the graph bends to the right, to the left, pardon me there. So it has to be here, okay, and also here. This one and this one, they have remained the same as what we are having here. You see that? So those ones will be off. So our answer is either B or C. Are we there? Now let's go to these reaction pathways. When you look at this one here, the activation energy has increased. When you increase the temperature, activation energy doesn't increase. No, it is the molecules that absorbing that energy. So they are having energy that is greater or equal to activation energy, such that when they are colliding, they can result into a successful collision and then they react. You see that? So we take this one with the same what? Activation energy as this one given here. You see that? So that means our answer is going to be a C here. As simple as that. Question 3. The equation shows the overall reaction between an amine and an acid chloride. This is the reaction here. When you get an amine plus an acid chloride, actually you will study this in A-level chemistry, okay? Then here you get an amide. An amide has this amide link here. Nitrogen, okay? And then here we have an arrow group. So this is what we call the amide link. Then from there, then we get this other salt there. Now, they're saying the 4 steps in the mechanism are as follows. Here they give them to us here. So this one donates. The nitrogen here has gotten a lone pair, so it donates. Remember, this oxygen here has to be partially positive, partially negative, then carbon partially positive, because oxygen is more electronegative. So it tends to pull the bonding electrons towards itself. Okay, so something like this here, they never put it. Okay, now after this, when this one donates the electrons on the carbon, this pi system is going to break. Okay, and you have something like this here. This nitrogen here has gotten a plus charge because it seems to have lost electrons here to give them to what? To the carbon. You see that? Then what else? When you go to 2, then oxygen here now donates the electrons back here, and then the chlorine gets off. Then after that, this hydrogen here is lost from this nitrogen. That is when chlorine comes for it here. Okay, but actually, yes, when the hydrogen is lost from here, it goes and then attaches to the chloride. And then you have our answer here. Then here, since we have many more molecules of this ethyl amine, it can continue to react. So this one can react with the excess HCl that is there, and then you form a salt. Okay, this is an acid-base reaction. Not so, because this one can donate a lone pair of electrons. Okay, and then you can scoop this hydrogen from here, you get this salt here. Okay, now let's look at what they're saying here. Which steps are Bronsted-Lowry acid-base reactions? So for Bronsted-Lowry acid reactions, we have to see one donating a proton. Okay, when you look at one here, they are donating what? Electrons. You see that? Even here, electrons are being donated. Okay, but here, when you look at 3, a proton is being removed from here. You see that? This one, the nitrogen here has lost the proton. So this is an acid-base reaction. We are looking at donation of a proton, then donation and then acceptance of the proton. Okay, then also here, you see that? So that simply implies that we are having 3 and 4, and that means our answer is what? Is B. Question 4. Chromium is present in compound X. 2 moles of compound X react with exactly 3 moles of silicon. The only products of this reaction are 4 moles of chromium and 3 moles of silicon compound, in which the oxidation state of the silicon is 4. Okay, then chromium and silicon are the only elements that change their oxidation states in this reaction. What could be the identity of X? So what I'm going to do is to get all of these ones here, this chromate here. Okay, then I react it with, they said 2 moles of compound X, so 2 moles. Then you react it with 3 moles of silicon. 3 moles of silicon. What do you get here? The only products are 4 moles of chromium and then 3 moles of compound, of the compound, of a silicon compound in the oxidation state of 4. Okay, so 4 moles of chromium, then plus, what do we get? The other one is 3 moles of silicon compound. Then the silicon compound is going to be with oxidation state 4. So silicon 4, oxygen is in 2. So what will you have? Silicon 4 oxide. So you have a 2 here and then a 4 here. Then this one reduces. The silicon 4 oxide is written like that, Si2 and then O2. So we shall have O2 here. Let's see, is this one balanced? This one is 4, then 4, 3, 3, oxygen 6, which is balanced. So it looks like the answer is A, but let's try others. Let's look at this one here. You have chromium 2, hydrogen 6, and then this one is going to be 2, then plus 3 of silicon, and then here you're going to have 4 chromium, and then plus what we have in here. Now, here, there is something we need to know. I would have written, let's say these are 3 moles of silicon tetrahydride, okay, because silicon has to be with this 4 here. Okay, the oxidation state. Now, in here, the oxidation state of hydrogen is -1, and also here still -1. Then silicon here is 0, and then the oxidation state here is a +4, so that means silicon has been oxidized. You get it? Then chromium here is 0, and then here, what are we supposed to have? We are supposed to have what? Is this one? No. Pardon me here. Chromium here, we have 2n, then plus 6 times -1, which is equal to what? 0. The -1 is for hydrogen, okay? And there are 6 of them. So I'm looking for the oxidation state of chromium. This is 2n, which is equal to 6. That means n is equal to +3. So here you are having a +3. So after having that +3, when you look at the right, what do we have there? This one is a 0. So this is reduction. Chromium has been reduced. And then this one here is oxidation. But again, removing hydrogen. What is oxidation? Oxidation is gaining of oxygen, not so? Or removal of hydrogen. Are we there? Removal of hydrogen is oxidation. Now here we have removed hydrogen from this, which is supposed to be oxidation. But then we see that this one becomes what? Reduction. So this one has to be off. Okay? We shall pull off this equation 2 here. That one has to be wrong. Then we go to this one is also the same thing. It has hydrogen and what? And it is chromium and then hydrogen. So when silicon scoops off the hydrogen, it is supposed to be oxidation, but we are seeing a reduction process in there. Okay, then when you come to this one here, chromate, when you remove the oxygen from here, remember this one is supposed to be 3. Okay, we are putting a 2 here. Then you get 4 chromium, and then you get, it has to be 3 moles of the silicon compound, which again has to be that. But look at the balancing. 4 times 2, that is 8 for oxygen, and this way we are having 6. You see? So it is not balanced. Okay? Not balanced. So this one is off. That's why we are taking our answer to be what? A here. Question 5. The reversible reaction shown is in equilibrium at the temperature of 450 degrees C. We have hydrogen reacting with iodine to give us hydrogen iodide. It is an exothermic reaction. The enthalpy of reaction is -9.5 kilojoules per mole. The table shows the equilibrium concentrations in the reaction mixture. These are the ones here. Then the temperature of the reaction is increased at the constant volume. When you increase the temperature, you are going to favor the backward reaction. Okay, so the backward reaction is endo. Because this one is a negative, that means the forward reaction is exothermic. So what they always put here represents the forward reaction. Are we there? If it's negative, then the forward reaction is exo. If it is positive, then the forward reaction is endothermic. Are we there? So since the forward reaction is exothermic, then the backward has to be endothermic. So when you increase the temperature, you are going to favor the endothermic reaction, which is the backward. So you expect the concentration of hydrogen iodide to decrease, and then the concentration of iodine to increase, and also the concentration of what? Hydrogen to increase, because equilibrium shifts to the left. Are we there? Very good. Now let's continue. So I'm going to have my hydrogen here. Then I have iodine. And then this side we have hydrogen iodide. So at equilibrium, before increasing the temperature, those are the concentrations we have. So we have 1.02. And then here you have 0.02. Then this way you have 0.98. Now, after increasing the temperature, they are saying that the concentration of one of the components falls to this. Which one do you think it is that is going to fall? It has to be the concentration of hydrogen iodide. Remember, the equilibrium has shifted to the left. You get it? To the endothermic reaction side. So that means this one is going to fall. Now it is the one that goes to 0. What? It is the one that goes to 0.8 moles. That means there is something that gets off from here, 0.98. No. Pardon me here, 0.80. Now, what went this side is what we need to find out. So 0.98, when you subtract 0.80, you actually get 0.18. Are we there? Now, this 0.18 here, it will come to this side, but it will be halved. Why is it going to be halved? It's because when you look at the reaction mole ratio, here it is 1 to 2. So when you are moving from this way coming to this way, it comes to a half, because this one here is a half of the 2. Are we there? Okay, so we are going to have this 0.02. Then we add a half of 0.18. That will be the new concentration of iodine. Are we there? Then how about the concentration of hydrogen? It will also be 1.02. Then we add a half of 0.18. You see that? Now, this one here, a half of 0.18 is 0.09. So if you have 1.02 and then 0.09, when you add 2 plus 9, you get 11. So it will be 1.1. And 1.1, that has to be the new concentration of what? Hydrogen. Remember here they said what is the concentration of hydrogen in the new equilibrium mixture? That is 1.11. So the answer is C. Question 6. The first stage in the industrial production of nitric acid from ammonia can be represented by the following equation. This is the equation. Using the following standard enthalpy change of formation data, what is the value of the standard enthalpy change for this reaction? Here we are given the enthalpies of formation of these compounds. Okay, now what we do, I'll put this one down here. 4 moles of ammonia reacting with 5 moles of oxygen, and then they are giving us 4 moles of nitrogen monoxide, then plus 6 moles of water, actually steam because it is gaseous. But these ones here are coming from enthalpy of formation. First of all is the energy change, okay, when 1 mole of a compound is formed from its elements in their standard states, okay, at standard conditions. Now we are going to have nitrogen. Nitrogen exists as a diatomic gaseous molecule. Then we have hydrogen, because we can see hydrogen in here. We can see hydrogen in here. Even hydrogen exists as a diatomic molecule. You see? Then also oxygen, the same diatomic molecule. So I'm having this one here for the elements in their standard states. Now, from here, we are forming ammonia. You see, but nitrogen here is 4. That means I can multiply this one by 2 to get the 4 nitrogen. And then the enthalpy of formation of an element is always 0. So there, I'm not going to put the arrow. Then we are forming this nitrogen monoxide, and nitrogen here is 4. Even here it is 4. Then oxygen, we can see here it is 10. So I'll put a 5 there. I'm going to put a 5 here. And then water, hydrogens are 12. So I'll put a 6 here. And even here, hydrogens are 12, so 3 times the 4. You see that? Now, I think I need to put off this. Yes. Now, look at this one here. Here, we are forming 4 molecules of ammonia. That means you have 4, then times the enthalpy change of ammonia, which is negative 46.1. You see that? This is the enthalpy of the reaction here that we are looking for. And then we are forming this one here, nitrogen monoxide. but 4 molecules are being formed. So we shall have 4, then times the positive 90.3. You see that? And then here, for water, we shall have 6 times, because from enthalpy of formation, we are looking at formation of 1 mole of a compound, and these are 6. So that means you have to get the enthalpy of formation and you multiply by the number of moles that are being formed. Okay? Now, using the Hess's law, I can move like this. So this one, that comes and joins here, now adds to this one, then to give you these ones that are actually going in the opposite direction. So I always say that we can use what we call clockwise. If you're doing physics, you know that clockwise moments are equal to anti-clockwise moments, right? So we are going to have 4 times negative 46.1, then plus DHR, then this one is equal to 4, because these ones, for them, they will be coming like that, and then these 2 will be coming like this, so you equate them. So 4 times positive 90.3, then plus 6 times negative 241.8. So what will be our DHR? Our DHR will be equal to the 4 times 90.3, then plus again 6 times negative 241.8, and then bring this on this other side. But since there is a negative here, then it is going to become a positive, right? So I'll just put plus 4, then times 46.1. So what will be our answer here? 4 times 90.3, then plus 6 into negative 241.8. This is 1.8. Then we have 4 into 46.1. And this one gives us negative 905.2 kilojoules per mole, and our answer has to be a C here. Question 7. The gaseous compound Z decomposes on heating. In the diagram, Boltzmann's distributions for Z at 2 different temperatures, P and Q, are shown. The lines X and Y indicate activation energies for the decomposition of Z with and without a catalyst. These are the ones here. Okay, they are saying which curve and which line describes the decomposition of Z at a higher temperature and with a catalyst present. Okay, at a higher temperature, this curve has to bend to the right. Okay, the number of molecules with the average energy has to reduce. Why? Because when you increase the temperature, we are going to have now very many molecules having what? Higher energy compared to that of the activation energy. So molecules with energy greater or equal to activation energy, they are going to increase in number. That means the ones that we are having just the average energy, they are going to reduce. They are going to be very few. You get it? So it's like when you are doing a paper and there is a pass mark that has been put. A pass mark is, let's say, 70%. And very few students have gotten the 70 and above. And then the teacher tries to reduce the pass mark and maybe puts it on there. That before even that, we are having very many students that are below the 70%. Now, if the pass mark is reduced and then you come to 60%, okay, that means the number of students from 60 and above is going to increase, but the number of students with 60 and below is going to reduce. That is why this peak here for those molecules with average energy has to reduce when you increase the what? The temperature. You get it? So for that case, Q is the one when you increase the temperature. Are we there? So they are saying higher temperature, it has to be Q. So we have to look at C and D. Okay. Now with a catalyst increases the rate of a chemical reaction by providing a pathway with the lower activation energy. It doesn't lower the activation energy of a reaction, but it provides a pathway with a lower activation energy. So if this one here is, let's say, the activation energy of the reaction, you are going to see that you have very few, okay, very few molecules with that energy. Now, when you bring a catalyst, then the energy here, the activation energy here, based on the catalyst, is going to be lower. So now you will have more molecules that can react. You see that? So it has to be X. We always put this line representing the activation energy of the catalyst. So with the catalyst, then we have to find it as X here. So our answer has to be here. X catalyst present. So that means the answer has to be a C. Question 8. The structure of a molecule found in food is this one here. It looks like that of glucose. Those who are doing biology, you know that better. 4 statements about the molecule are listed. This molecule contains only sigma bonds. This is true because there is carbon here. We are seeing single bonds here. You can see there is a hydrogen here. So this is one single bond, another one here, another one here, another one here. All of these ones are single bonds. If there is a double bond or a triple bond, then we'll talk about the pi bonds there. You see that? So that is correct. The molecule contains pi and sigma bonds. This one is off. We are not seeing any pi bonds, okay? The 6-membered ring is planar. The 6-membered ring is actually not planar. When it is planar, that means the atoms are in the same what? Plane. You see that? They're in the same plane, but we see these ones are vertical. This one, it is like a chair, okay? The way you look at a chair is like this. I don't know whether my art is okay. You pardon me if it is not. You can draw yours, which is good, which is better, right? So something like that. It is in the chair format. So some are going down this way, then others are going up this way. Then we are seeing the horizontal here. So that is how it looks like, okay? So we are not going to have this one as planar. It's not planar, okay? And then the 6-membered ring is non-planar. Actually, this is it. So that means we have 1 and 4, and therefore the answer has to be B. Question 9. In which substance are covalent bonds broken as it melts? Now, silicon here, for oxide, it actually has a structure that resembles that of diamond. So we have silicon here. It has a tetrahedral structure. So you have oxygen continues. Remember, it is supposed to have 2 bonds. Okay, so this one can connect to, again, silicon here. Okay, even here, then it continues like that. Okay, each oxygen continues with 1 more. Like that, it continues. Okay. So when you are melting this, remember, you are going to have this silicon 4 oxide now becoming a liquid, and it has to be this one here. You get that? As a liquid. Now, that means you're going to break these covalent bonds such that you have silicon with the two oxygens. You see that? So the answer actually has to be this A here. When you melt ice, you are going to get water, but what you are actually breaking in water, you are having oxygen and then hydrogen. Then these ones are partially negative, actually positive, because they tend to lose the bonding electrons. Oxygen, which happens to be much more electronegative. So this one can form a hydrogen bond with this one here. So like that, partially negative, then this is partially positive. So this thing continues, okay? So when you are heating in here, you have to break the hydrogen bonds completely, okay? Now here, we are not going to break the covalent bonds. Why? Because the covalent bonds, we have oxygen and hydrogen. Those ones are not going, these ones here. This is hydrogen bonding is the one that we are going to deal with first, not these ones here. That means water is off, You see, because what we are breaking is what? The hydrogen bonds. And then when it comes to iodine, for iodine, here when it is melting, we are having, these are ID forces, okay? Those are the ones you are going to break in there. You see? Hey, they are also, but we are not breaking these covalent bonds here such that we get what we call atoms. No. So even this one is off. Then in ethanol, just like this one for water, there is going to be hydrogen bonding, and you are also not going to break the covalent bonds between the carbon and the hydrogens and the oxygen in the molecule. So that means this one has to be off. So the answer has to be A. And then question 10, why is the second ionization energy of sodium larger than the second ionization energy of magnesium? Now, let us look at sodium. Sodium here has gotten how many? How many protons? 11. So that is 1s2, 2s2, 2p6, then 3s1. And then they are saying second ionization energy, okay? So I'm going to use sodium here plus. So it has lost one electron in its outermost shell, right? So I'll put off that. And then magnesium. Magnesium is 12. So 1s2, 2s2, 2p6, then we are supposed to have 3s2. But since we are looking for the second ionization energy of magnesium, that means it has lost already one electron in the outermost. So here we shall have 1. So we have this one here, plus 1. Now, when you look at this one here, there is one more shell there. That means the shielding effect here is greater in magnesium compared to this one here for sodium, okay, for sodium ion. So this simply implies that when you are removing an electron from here, the sodium ion, you are actually removing it from a full shell of electrons. That is nearer to the nucleus, so you are going to face a lot of resistance. You see that? Because the nuclear attraction there is stronger. But here, because of this one more shell, the shielding is bigger, okay? So here, when you are removing from here, you are only shielded from these two. You see that? When you are removing from here, you are shielded from these three. So the shielding is bigger here. You see that? However much the nuclear charge here is bigger because it has more protons. But the more the shells there, and you get bigger shielding, the shielding is repulsion between these electrons here. Okay? So the more the repulsion, the longer the distance between the outermost shell electrons and the what? The nucleus. You see that? So that shielding outweighs the nuclear attraction, or the nuclear charge. You see that? And then the nuclear attraction is going to be weaker. So they are saying the attraction between the nucleus and the outer electron is greater in sodium than in magnesium. That is right. The answer has to be A. It is stronger here because you are nearer to the nucleus, okay? Here there is much more shielding, you see? But let's see what they are saying in B. The nuclear charge of sodium is greater than the nuclear charge of this magnesium ion. No, the sodium has less number of protons compared to this magnesium here. So get the difference between the nuclear charge and the nuclear attraction. The more the protons, the greater the nuclear charge. But then the nuclear attraction is going to be determined by now the shielding effect. So the greater the shielding, then the smaller the nuclear attraction. You see that? Then C, they are saying the outer electron of sodium is more shielded than the outer electron of magnesium ion. No. From here we are seeing the outer electron here, it is shielded from 2 here. But here we are having 3. You see that? So that one is also wrong. And then when we go to D, the outer electron of sodium is in the same orbital as the outer electron of magnesium. Now, is in the same orbital. This is true because this one can be 3s1 for sodium, okay? Then 3s2 for magnesium. The outer electron is here. It is in 3s2 and also here 3s1. But this is not the explanation for the second ionization energy of sodium being larger than that of what? Magnesium. It is right, but it is not the correct word explanation of what we need. Okay, so that means our answer is going to be A.